Good afternoon and welcome to the first technical session of SIBGRAPI 2020. I'm Manuel Oliveira from the Federal University of Rio Grande do Sul, and I'll be your host in the session, which contains 5 very nice papers covering a wide range of subjects in computer graphics, ranging from multi-style transfer to hydrographic printing, virtual humans, volumetric rendering, and real-time indirect lighting. So I hope you'll enjoy. You can post your questions to the speakers, either through YouTube or Wova, and we'll be glad to ask your questions in your behalf. So the first paper of the session is entitled Selfie Art, Interactive Multi-Style Transfer for Selfies and Videos with Soft Transitions. The paper is co-authored by Lucas Alegre and Manuel Oliveira from URGS.
Hi, I'm Lucas Alegre, and I'm going to present Selfie Art, Interactive Multi-Style Transfer for Selfies and Videos with Soft Transitions. Imagine that you took a beautiful photograph like the one shown here. What would this photograph look like if we transfer the style of a famous painting to it, such as the Starry Night from Van Gogh? Well, the photograph now looks like it was painted by Van Gogh himself, but it still preserves its structure and main elements, like the buildings. And now, what about if we used another painting from different artists? Well, this kind of results can be achieved since the remarkable work of Leon Geddes on neural style transfer. The key idea here is that we can separate the content and style of an image using a convolutional neural network. Since then, faster methods have been developed, allowing for style transfer in real-time applications. They have also been combined with semantic segmentation models, where it's possible to transfer the style in predefined segments. It is well known that selfies are the basis of many social network interactions nowadays, such as Messenger, Instagram, Prisma, and Snapchat, where it's possible to play with filters and special effects. Also note that semantic segmentation models can also be applied to faces. In this sense, the semantic segments can be the hair, the clothes, the background, the eyes, and so on. In this context, we propose Selfie Art, an interactive multi-style transfer method. With Selfie Art, user can select the desired segments for which a given style must be transferred to. While so, the user can control the smoothness in the transitions at boundaries of the segments. Next, a different style can be applied to another set of segments, allowing for simple and creative exploration. Selfie art, however, is not limited to portraits. Selfie art can also be applied to videos. Here, the style is applied to each individual frame while preserving temporal coherence. Our contributions include a technique for interactive multi-style transfer of portraits and videos, which is based on semantic segmentations of facial elements, where each facial element may receive a different style, and a method for blending the multiple styles with adjustable softmasks. They are built from probabilities provided by the segmentation network and can be adjusted by the user in real time. Given a selfie as input, a face parsing neural network performs semantic segmentation of the facial elements. From a set of style images, a style transfer algorithm can be used for style extraction. The user then interactively associates the styles to the segment elements of the image. For instance, style A can be applied to the clothes, the style B to the face elements, and style M to the background. The user also defines a desired smoothness level, which is used to create the soft masks. The soft masks avoid abrupt transitions between stylized regions, which would be introduced if regular binary masks were used instead. By combining the selfie and the styles using our proposed soft masks, the result is a selfie with multiple styles and soft transitions between stylized regions. The same process applies to the case where the input is a video selfie. Then the style is transferred to each frame individually, and the result is a stylized video selfie. Here, we show the use of choose style transfer to create artistic portraits. Each portrait combines the styles from corresponding rows and columns. The possibilities of creative exploration are only limited to the user's imagination. Now we are going to show some video examples demonstrating several combinations of styles. Introducing Mr. Obama.
Hi, everybody. Anaya, thank you for that beautiful introduction. Hi, everybody. Anaya, thank you for that beautiful introduction. Hi, everybody. Anaya, thank you for that beautiful introduction. Hi, everybody. Anaya, thank you for that beautiful introduction. Hi, everybody. Anaya, thank you for that beautiful introduction.
The source code for selfie art is available on GitHub with the following link. Thank you for the attention.
Not yet. Please feel free to submit your questions to Lucas. So Lucas, considering the fact that doing all the processing that you described in your paper, you can't quite do it yet in real time for videos. What do you see as the main restrictions for achieving multi-stylization of videos in real time?
Hi, thank you for the introduction, and hello everyone. So it's a good question. In fact, theoretically, both methods that we use, the multi-style transfer algorithm and the segmentation network, they both can work in real time for videos. But as we are using them simultaneously and sequentially, they end up not achieving real-time performances. In fact, for the videos that we have shown here, the Obama video, we can achieve 7 frames per second. And one way that we can improve the result is by making the pipeline in parallel. So we can perform the segmentation of the frames and the stylization in parallel, and maybe then we can improve the quality of the speed.
Okay, thanks. So there is a question here from Renan Luigi. What is the average overhead time on the processing of those filters?
Okay, so as I mentioned, for the Obama video, as shown here, we can process 7 frames per second, and the segmentation network, it's much more faster than the stylization process. So the bottleneck here is the MSGNet, which I don't know, I don't have the numbers to say how much is lower is the stylization compared to the segmentation, but the bottleneck is definitely the stylization. So if we want to improve the speed and achieve real time performance in videos, there's room for improvement in the stylization methods.
But do you have any numbers to report to Luigi? In specifying, for instance, for a given hardware, you know, the one that you use, maybe you provide the specs and overhead, maybe milliseconds or.
Yeah. So the application that is shown, the desktop application, not for videos but for images, was recorded using a very slow notebook, in fact, with a Intel Core i5 CPU with 8 GB of RAM, and we not use a GPU, and we could perform all the pipeline in real time for images. But when we go for videos, with the maximum performance we achieved was 7 frames per second.
Okay, thanks. So, and are there any plans to? I know that you've made your source code available on GitHub, but are there any plans to make an actual app and make it available for the public?
Yeah, that's a very good question. It's something that I plan to do sometime, but to be honest, I'm not very familiar with mobile development, so I'm not very familiar how can I port the application to mobile, to Android or iOS. I know that I'm not sure if the libraries like PyTorch that we used can be easily ported, but it's something that I want to explore in the future. As you mentioned, the desktop application is available on GitHub. Everyone can test it by yourself, but it would be really nice if we can port it to mobile as well.
Okay, we have one last question from Marcelo Walter. He congratulates you for the work, and he asks how hard it would be to extend the work for the whole body. For instance, make the pants one pattern and so on.
Oh, nice question. The modification that we need to do in our method is only in the segmentation network that we need to extend the number of segmentation classes. And we need to have also a data set which fine-grained annotations for all the possible segmentation segments in the image. So for instance, in our method, we use a data set only of faces, of portraits, of celebrities. So of course, we cannot currently perform segmentation of paints, for instance, because it is not present on the data set. But training a segmentation network with more data using different classes and different kinds of images, it definitely would be possible.
Okay, so thank you very much, Lucas, and congratulations for the work. Receive our virtual applause, right? From the audience and so on. Now we have to move to the next paper. It's entitled Real-Time 3D Position-Based Dynamic Simulations for Hydrographic Printing. The work is by Leonardo Thomas, Cal Agüero, and Antonio Apolinário Jr. from the Federal University of Bahia. And Leonardo Thomas will present the work.
Hi, I'm Leonardo Thomas, graduated in Computer Science at the Federal University of Bahia. I will present a real-time 3D position-based dynamic simulation for hydrographic printing. I would like to start talking about 3D printing and hydrographic printing. Today, it's possible to reproduce complex objects with 3D reconstruction and 3D printing. Let us see this 3D object. And this one is the same object reconstructed in 3D. And this is the 3D printed object. As we can see, today it's possible to reproduce physically a 3D model with a well-known process. However, to reproduce physically a 3D model with colors is a hard task. Among the methods for coloring a 3D model, we can highlight a decal-based technique called hydrographic printing. Hydrographic printing is a viable way to color a wide variety of materials like ceramic, glass, plastic, wood, and metal. When we use hydrographic printing, we can print the color pattern in the film, and we put this film floating in the water. The film reacts with an activator and becomes a thin sheet that carries the ink of the printed pattern. After that, we dip the object in the water and the object touches the film. The film stretches and adheres to the object's surface, coloring it. This is the final result. It's very common to use hydrographic to transfer repetitive patterns to the object. If the goal of hydrograph is to map a texture to the object, like a texture map do in a computer graphic model, we will face difficulty of map the hydrographic theme to the physical object. This is a limitation in the process, and is the main challenge in this work. It's possible to simulate the hydrographic printing process in an efficient way. Possible, the result of the simulation, we can find a way of applying in the physical hydrographic process. In the previous works, we can see the soft body simulation with the finite element method in the CPU. In contrast, this work addresses the soft body problem with position-based dynamics and model the film interaction using a collision rendering approach with spatial division in the GPU. In a few words, the main contribution of these works is a GPU-based approach to the hydrographic problem. This allows us to run the simulation in real time. We believe that a real-time simulation can give a better support to the hydrographic technique by giving immediate feedback, opening new possibilities. For example, we can simulate the immersion with different positions and choose the one that uses a larger film area and a low film stretch.
Thanks, Leonardo. I don't see any questions at the moment, so I'll start with my own question. So, Leonardo, how does the technique handle, say, singularity points? For instance, when you have a sphere and you put it on the water, and I could see this in your longer video, right? Then the film will adhere to one pole of the sphere and cover part of it, go to the equator. How about the second pole? I mean, how would you handle this? Would you have to place the object twice and kind of hope that the textures are gonna align in the two trials? How does it happen?
Yes, it's a good question. There are many approaches to resolve this problem to cover all the model, but we use multiple immersions. And so in the case of the total, we immersed first the back and after the bottom. And we have the problem to align the model very precisely with a hardware setup. And this is a real problem in this approach. Yeah? We have to align the model, and we have to develop a good setup, a good hardware to align the model and make two immersions and cover all the model.
Okay, thanks. So there is a question here from James Game. He asks, how did you validate your simulation?
How I validate?
How did you validate your
validate.
simulation? Yeah.
Oh yes. Well, we take as ground truth models covered with a checkboard pattern like this, like this. Can you see? Can see.
Yeah. Yeah.
So we make the hydrographic printing with the real models as ground truth, and we make the same simulation to the same models and the same positions, and we take pictures and we check the specific points in the pattern if they are aligned. So we measure the error in these points, and we take statistical measures to measure the error.
Okay. One thing that I could notice is that the angles in the checkerboard pattern, they were not locally preserved, right? In this mapping, is there any thing that you could do or suggest in order to preserve, for instance, in the case of the checkerboard right angles, we could see that some of those patterns got a little bit distorted.
Oh, if I understand, we in this work we observed that the best condition to use the hydrographic printing is to avoid a high stretch in the film. So we analyze the shape and we choose shapes that are with a low stretch. Regions with low stretch are very is very good to use hydrographic. And in other situations, we avoid shapes with a high stretch.
But regarding the angles, I mean, is there anything that, given that you know the shape in your simulation, can you take the shape into account to avoid, for instance, that a right angle, for instance, in the case of the checkerboard pattern, I mean, get distorted, and instead of being a 90-degree angle, it becomes somehow maybe 60-degree or 120 or so. Can you take this into account in your simulation?
No, we don't consider. I'm not understanding very well. But in the simulation, we consider the contact points and the film and the object, the angles. How do you see the angles? The tangent angles when the object touches the film. I don't understand very well these angles.
Okay, and so how about I don't see any other questions from the audience, so let me ask you one more. How can the technique handle, say, non-convex objects? If you have objects with concavities, arbitrary shapes that are not non-convex, how would the technique handle this?
This technique is not a good technique to face non-convex object. Um, this is a limitation. This is an important limitation of the technique, and we have other techniques that can achieve good results with this object with a complex uh, occlusion points, occlusion regions. And hydrographic is good for some kinds of objects, but can be not so good to other kinds of objects. And we have to understand uh, the objects that are very as better good the objects that the technique can works very well, and we have to use other techniques to achieve good results.
Okay, so thank you very much, Leonardo, and receive the applause from the audience. We have to move to the third paper of the session. It's entitled "Towards a Legion of Virtual Humans: Steering Behaviors in Organic Visualization." The paper is by André Antonich and Soraya Mus from PUC, Rio Grande do Sul, and Luiz Henrique Figueiredo from IMPA.
Hello, I am André from UCRS, Brazil, and I will be presenting our work towards a legion of virtual humans steering behaviors and organic visualization. Many methods have been proposed to simulate crowds of humans. Typically, agents are simulated individually, said to be a microscopic simulation, having their actions and behaviors applied individually. Microscopic crowd simulation methods have been proposed to simulate aggregated motions of people, usually at an accuracy performance trade-off. We propose a multi-level simulation method to crowd simulation and a novel way to visualize densities of crowds. The granularity of the model dynamically adapts to the simulation environment. We also aim to provide a more organic visualization for macroscopic crowds. Several microscopic approaches have been proposed, like social forces, optimal reciprocal collision avoidance, and biocrowds. Several macroscopic models, such as continuum crowds and bioclouds, have been proposed also. Hybrid models combine both approaches. Strong et al. Combined continuum crowds and the RCIA model by defining regions to be simulated with each model. Among these models, we highlight bioclouds and biocrowds as spatial competition algorithms, where entities compete for space discretized in the form of space markers. We chose these algorithms because of their inherent relationships to the model entities as owning space. Legion is a new macroscopic abstraction for crowds. The model sees crowds as groups of individuals, which compete for space and can split and regroup like real-world groups. These split and merge behaviors dynamically adapt groups to environments. Our proposed blobby visualization aims to provide a more organic visualization for macroscopic crowds. Implicit surfaces are a standard technique to visualize density data. Our approach represents crowds as density fields using a global blobby model. We simulated a set of experiments to compare how the complexity of the environment affects the emergent behavior of splitting and merging, as well as the average behavior of the crowd. We simulated crowds as legions traversing a scenario of obstacles. And here you can see some of our results.
Okay, so please submit your questions to André. While we wait for questions from the audience, let me get started here. So André, we see that the split and merge operations, they happen in response to some obstacles in the environment. Are there any other factors, for instance, other maybe environmental elements that also impact these actions?
Yeah, there's also other legions, of course. So since they are competing with for space that a legion cannot obtain in a future frame or a future time step, and that's something the user can adjust, like how how long in the future that happens. That's also taken in consideration. So a legion competing with other legions will eventually like split. Say a bigger legion is in front of like a group of people, so they split to like go around the bigger legion. That can happen, and also obstacles. So.
And any other, say, environmental things, like for instance, the topography of the terrain, even if it's not a mountain, but if it's some irregular terrain, would that affect somehow the way the solution works?
We haven't like took in consideration the topography of a scenario at the moment. Our experiments are all, and our model basically assumes the ground is a plane. So that's not currently in the model.
I see. So, folks, please submit your questions to André. André, one thing that I could note in the experiment that you showed there, where there was this heat map visualization, was that there were some color changes, especially in the small legions, in the small blobs. They change it, say, from purple to greenish or so. Could you comment on that? Why did that happen? What is the meaning of that?
Yeah, we are measuring how much area each legion has. So if a legion represents 50 agents or 5 agents, let's say 5 agents because the smaller ones are probably around that. If it represents a certain quantity of agents and it captures some region of space to determine its density, and then we basically check if it has to split or merge again. And if a legion is, say, near an obstacle, it probably has less space than it requires to basically maintain its desired density. And that happens pretty often soon after like split operations, because the bigger legion splits for a reason, right? It didn't have enough space, so it splits, and the smaller outer legions can like spread apart and open space for the inner ones, or the legions which are basically touching obstacles, to actually move around and accommodate in space. So soon after a split operation, the legions which are in a position closer to the obstacles show some increase in density, but that's probably a side effect, I think, of how the split operation works.
Okay, so James Gain asks, I note that part of one of the legions got stuck on an obstacle in one of your videos. Do you have a way for handling this?
Yeah, we were using like very, very simplistic path planning, just because we didn't want to overcomplicate the movement of the blobs. But usually we use like a more complicated path planning, or say A star, so that the blobs, the legions wouldn't like get stuck behind obstacles. But we were trying to make them basically collide with obstacles, and it would be counterproductive to having them also avoid obstacles.
Okay. Carla Freitas asks, can you keep a group separated from the legion for a longer time, or the sublegions always merge?
Yeah, one of the parameters a user can adjust is how long after a split a group will take until it like can merge again. And if that's a like really short time span, usually the blobs will eventually split and then merge again and split, and then it can lead to like some erratic behavior. For our experiments, we used like 15 frames, but the user can play around with that parameter for like to generate a simulation which is more, it's closer to what they desire for the situation or model.
Okay. Could you please comment on possible, say, limitations or situations for which you think that the proposed approach would not be, recommended or the most appropriate one?
We actually we have some issues we kind of want to solve. We cannot guarantee that the area the blobby visualizations occupies respects the density the crowd would be occupying. So we cannot basically guarantee that the region it occupies stays the same. It can be slightly smaller or slightly bigger, depending on the threshold values for the blobby visualization functions. So that's one caveat. And so the user also have to kind of adjust the parameters for the threshold values. So yeah, I think that's what I can think right now. We debated so many other situations that would be both good or bad for a simulation like that. That's
okay. So thank you very much, Andre. Receive the applause from the audience, this virtual applause. Thank you very much. And now we move on to the fourth paper of the session. It's entitled "A Bucket LBVH Construction and Traversal Algorithm for Volumetric Sparse Data." This paper is by Igor Fernandes and Marcelo Walter.
Hello and welcome. My name is Igor and I'm a master's student from Roots. We will briefly present you an overview of our paper, A Bucket-Led BVH Construction and Traversal Algorithm for Volumetric Sparse Data. To understand what our problem tries to solve, we will first present an example of sparse volumetric media, as clouds. On the left, we have a reference photo by Kevin, and on the right, a three-dimensional representation of it, both with and without its bounding boxes. So we are after a technique to traverse this data, which is comprised of voxels. We need to traverse the grid to compute the volumetric render equation, and traversing through the grid without any acceleration structure is expensive. More precisely, it costs us O(n) to the power of 3, where n is the dimension of the grid. We use a linear bounding volume hierarchy, LBVH for short, to improve performance, reducing the problem from a vector trait tree linearized in memory, reducing our costs to O log n. We present a stackless and pointerless bucket linear bounding volume hierarchy, BLBVH for short, that can be easily ported to shaders. Being able to run on shaders presents a lot of advantages, such as being portable for any system that supports said shader language, be it HSL or GLSL. We group voxels in buckets by the Morton codes. When analyzing the problem using Morton codes, we are able to keep data locality while also being able to use better data acceleration structures. And by grouping voxels into buckets instead of bricks, we make the construction much faster and flexible. And when organizing by buckets, it becomes much more flexible as it allows for more arbitrary sizes and it contains exactly the necessary amount of non-empty voxels to test. A very quick summary of how we construct the tree is that we encode all non-empty voxels using Morton codes and sort it. We fill these buckets with these sorted Morton codes, remove empty buckets and shift to the left, map each bucket to a leaf, and then calculate the AABB of each leaf and propagate upwards. The traversal is done in a classic depth-first search fashion with minor modifications. Before doing any intersection test, we must verify if the current node is empty. In the figure, we have a demonstration of how we would traverse a tree with Morton codes on the range 0 to 64. A detailed example is done step by step in the final presentation. We tested with 6 grids of small to medium size. For this presentation, we selected the results from the 3 largest grids. We improved construction speed by 9 times on average, compared to our reference implementation of Zelman and colleagues. We also improved traversal speed by 2 times on average for bucket sizes of 4. Here, we show the traversal performance for the 3 largest grids we tested on. The larger the bucket becomes, the less traversal performance we get. It occurs because for larger buckets, we need to do more intersection tests in a row, compromising performance. Since we store Morton code for each non-empty voxel and an offset for each bucket, our memory overhead is higher than our reference. Due to limitations in shaders and real-time applications such as games, we conclude that this trade-off may be of interest in cases where more frames per second is the main goal. The caveat is that the smaller a bucket, the more it takes to construct the tree. It leaves us with a question: what bucket size to use them? We conclude that the best case scenario lies on buckets of size 64 and 128, where we still have better performance than our reference. Unfortunately, our memory overhead is still higher than our reference. We further discuss this in details in our presentation. Thank you. This is me, my advisor Marcelo, and we invite you to see our presentation.
Thank you, Igor, for the presentation. Please submit your questions to the speaker.
Good morning.
So,
Good afternoon.
yeah, so Igor, you showed us that traversal performance improves with smaller bucket size, but with a smaller buckets, then this increases the time to generate, the data structure, right?
Yeah.
So, well, so at first one would think, so, well, since the generation can be done offline, then we should always prefer a smaller bucket size. However, there is this memory footprint that is also an issue. So besides memory, I mean, the memory price that you have to pay for using smaller bucket size, are there any other aspects that you could comment with us that also should be taken into consideration when you're dealing in trying to find this balance between memory, performance, time, and so on?
Mhm. Yeah, the main concern here is the memory. There's not many others aside from that, but what really happens is that no, we could generate the grid offline, and thus, well, the construction time is just a pre-process step. But when we consider like animations or procedure generation, we should also take in consideration the construction time. That's why I emphasized on that too. But yeah, if you are just rendering a static grid in real time or whatever, the construction part of the problem is not that big. We could choose smaller buckets instead of larger buckets. So yeah, it depends on the user case mostly.
Okay. Any questions to Igor? So for those that are planning to use your technique, do you have any guidelines, to help them on choosing bucket size and all grid size and all that for applications? What would be your recommendation for them?
Well, for static grids, which you could use a preprocess, well, you could choose the smaller bucket possible, like size of 2 and 4. But for buckets for grids that are animated or procedurally generated in runtime, I recommend using a better balance of bucket size and traversal performance, something around 16 or 32 buckets per grid. But it depends on how sparse the grid is too. So it should be should have a test on this matter to see which would perform better.
Yeah, but so while we wait for questions from the audience, you said, for static grids, I would recommend using the smaller bucket size and so on, because you can, of course, pre-process the tree and so on. But there is an issue. You're using the memory of your GPU to store this data structure, right? So how do you balance this with other needs for memory? I mean, you need memory for textures, meshes, and other things. And so how do you handle this?
Oh yeah, I was thinking about a simple visualization program. So yeah, when we take in consideration the other memory consumptions that may come from the application, such gestures, meshes, and so on. Yeah, then I would recommend using like larger grids. I'm sorry, larger buckets, so you can balance better the consumption of memories. So yeah, it depends a lot on the application, but the rule of thumb here is the bigger a bucket, the larger, sorry, the less memory consumed, but the larger time it takes to construct the grid. So yeah, it depends a lot. It's much more on a per basis user or per base
Okay.
application.
And we have a question from Carla Freitas. She says, nice work. You say that your work is for sparse data. Do you have an estimate for the limit in density?
Um, by well, to limit in density, you mean like in resolution? I am be confused there.
Um,
Well,
well,
if she is
answer if it's based on resolution, if it's based on the number of particles there are in the grid, and I would guess this based on the density of those participating media that you have per cell of your grid. But that's my
yeah
guess.
yeah because for example, if we have let's say a grid with 100 by 100 by 100, but it's just 20% filled, the other 80% is basically discarded because when we have a voxel that's empty, I don't need to compute that. I only take in consideration voxels that have at least ND density. So yeah, it depends a lot.
Okay, so thank you very much, Igor. Also receive our applause, virtual applause here. We have to move to the last talk of the session. It's entitled Screen Space VPL Propagation for Real-Time Indirect Lighting. The work is by Vitor Aranha, Márcio Macedo, and Antônio Apolinário Jr. from the Federal University of Bahia.
Good evening, all. My name is Vitor, and today I'd like to present our paper, Screen Space VPL Propagation for Real-Time Indirect Lighting. I'd like to begin first with a summary, where we motivate our work and discuss related papers. Then, we enter the SSVP pipeline and discuss how the technique is actually implemented. Then we proceed to results and finally conclude this work. First, let's motivate our method. The key word here is global illumination, the light that bounces off the environment multiple times and creates a set of interesting effects, from color bleeding to mirror-like reflections. Reproducing the whole phenomena is quite expensive though, and real-time applications often pre-compute it. In this context, our work, SSVP, focuses on adding diffuse indirect lighting to the scene. Notice here its impact on the scene's sponsor in these pictures. Many work inspired us, but a few select ones are core to this research. Instant radiosity reformulates the rendering equation as an integration of the contribution from many virtual light sources, the VPLs, treated like infinitesimal surface patches. To bring instant radiosity to a real-time setting, reflective shadow maps elegantly use the rasterization pipeline to create VPLs in real time, rendering from the point of view of a light source. Imperfect shadow maps try to solve visibility for thousands of VPLs at interactive rates by rendering from the scene from the point of view of a point-based representation. Clustered visibility reduces the computational costs of these renderings by clustering VPLs and solving visibility for cluster centroids only. Sequential Monte Carlo instant radiosity improves temporal coherency of a VPL rendering by devising a placement scheme as a particle filter, allowing for grid coherence for both dynamic light sources and cameras as well. Now we enter the SSVP pipeline. First, an overview of the method. Screen space data is stored from both light and camera perspectives. Light buffers are then sampled and VPLs are placed on the world. These VPLs are then clustered and the visibility maps computed for each centroid. These maps are then sampled again, and the second bounce VPLs are then created with the projection-aware sampling scheme. The final scene then gathers contribution from all these VPLs. We maintain the pipeline in GPU as much as possible, approximate and aim at plausibility instead of accuracy, and for this reason, we can provide a real-time performance below 16 milliseconds per frame. Gbuffer rendering happens for the main camera and main light source. We store position, normals, and color information for both point of views. This step represents screen space data being stored. Then we sample the RSM texture with a uniform sampling method, or a low discrepancy sequence. We read the texture from each layer and store it in a GPU array, in our case, a shader storage buffer object in OpenGL. Then we clusterize the scene, with k-means performed in compute shaders. We reuse the same distance metric from DOM to avoid getting completely opposite normals pointing different directions. We store each cluster centroid as a VPL and keep track of the relationship between clusters of VPLs and its child VPLs. Next part, we render a few hemispheres of visibility for each cluster centroid using geometry shaders. Now, to sample second bounce VPLs, it's important to notice that unit box samples are wasteful. Therefore, we leverage the elliptic paraboloid properties. As you can see in the left, a unit box approach is wasteful. There are lots of samples that end up falling outside of the region. We use a disk sampling method based on the properties of the paraboloid we use to render. In this case, our paraboloid is not only elliptical but circular as well. This means that any cross-section, horizontal cross-section of this paraboloid defines a circle in the plane. This validates our method. Finally, shading happens by gathering contribution from each VPL, both first bounce and second bounce. Use interleaved shading to speed up the computations. Because diffuse lighting is low frequency in nature, we may get away without computing lots of visibility queries for second bounce VPLs. We now proceed to the results. We evaluate our method in two fronts, visual quality and performance. For visual quality, we compare our renderings to a path traced ground truth generated with Mitsuba Renderer. Then, we compare multiple cluster configurations to find out which one provides the best compromise between speed and quality using a perceptual metric. Performance here is evaluated in milliseconds per frame, aiming at times below 60 milliseconds for the entire pipeline. The relative percentile per frame is also provided. All tests were carried on a low-end Pascal GTX 1060 with 6 GB of RAM. We evaluate the algorithm in three themes: Sponza, Conference Room, and Cornell Box. But due to time issues, we will focus on Sponza only in this presentation. Visual quality first. See your method on the right, 2 bounces of light, and the path traced ground truth on the left. Notice nearby the curtains on the floor how we achieve similar levels of color bleeding. And to decide which cluster configuration offers the best compromise between speed and quality, we compare them using HDR VDP2 perceptual metric. The reasoning here is that the more clusters, the better, Therefore, we try to obtain a score of how close lesser configurations are to higher ones, to find out at which point we find diminishing returns. We now proceed to performance analysis. We average the time milliseconds for each stage of our pipeline in multiple frames for multiple cluster configurations. gbuffer here represents both camera and light view in the third rendering mode. Notice how the cost to render paraboloids grows steeply until 16 clusters. At this point, we fail to provide rates below the threshold of 16 milliseconds. The chart of the relative percentile of each stage illustrates better how the cost to render new maps grow very aggressively. Clusterization costs are almost negligible. We embedded it in the MISC stage with VPL sampling and shadow map rendering. Finally, we conclude our method. SSVP achieves a fast method for plausible real-time indirect diffuse lighting. We also extended real-time cluster-based techniques to allow for second-bounce VPLs. In this work, we favor visual plausibility and speed instead of accuracy. Now, our work still has place with the advent of ray tracing capable hardware. Rasterization still dominates the real-time industry, but with ray tracing, they might coexist: mirror reflections, ray traced shadows, and word space VPL propagation instead of screen space. Thank you for your support. And for further inquiries, please contact us at the email addresses in the screen.
Thank you, Victor. Please submit your questions to the speaker. So, Victor, you mentioned that you performed interleaved shading for speed up, right?
Sure.
Could you please explain us exactly what you mean by interleaved shading?
Oh, fine. This is a really good question. And this name, interleaved shading, actually refers to deferred shading of interleaved sample patterns. It's a paper that's become really important in the real-time industry, especially when you render with multiple VPLs. What you really do is that you tile the screen, your actual gbuffer, and you interleave the points you're shading. These tiles actually become these tiles actually become multiple smaller screens, and you shade subsets of these screens with different subsets of VPLs. And what really happens is that when you interleave, you gather all these tiles together, you actually for real has reduced the computational cost of rendering thousands of VPLs to a new set of subset of smaller sets of VPLs. And this actually speeds up the computation, makes VPL-based approaches feasible for real-time rendering.
Okay, thank you. And could you comment on possible limitations of the technique that you just presented?
Sure. Our technique relies heavily on indirect diffuse lighting. It's very low frequency in nature. Therefore, we cannot really represent caustics or mirror-like reflections, glossy surfaces. This is really limited to this atmospheric lighting, diffuse lighting that makes shadows more brighter and less pitch dark. It also adds a little bit of color bleeding, but this is all the scope that our works really focuses in.
Okay, thank you. Let me ask you one more question. I don't see questions from the audience. One thing that is actually not due to your technique, but one thing that called my attention is the fact that on the ground truth image that you showed, we could see some regions, some inner regions, inner geometry with darker shading. Whereas, I'm talking about the ground truth image. Whereas on the floor, it would look kind of more saturated than yours. The light is kind of saturating. Can you quickly and briefly explain us what was going on there, why it happened?
Sure. When the screen, the route screen we're actually using in this work was generated with the Mitsuba renderer using 256 samples per pixel in a path tracer, and we did not denoise the screen. The actual image synthesized was really raw, and that region you can see nearby the curtains, right? These regions you can also, without denoising, you can see the granular points that correspond to the color bleeding, and we actually let that image in the work so that people could see, that the public could see how the images differ. The path traces requires a strong denoiser to work, though it still can provide a very realistic image. Our work, however, works without denoising, no denoising. All the light that you can see is emerging effect of the multiple contributions of other VPLs, and therefore this was not it was an artifact, of course, of the rendering, but that was supposed to represent what two raw images generated by two different algorithms could generate without further post-processing.
All right, so thank you very much. You two receive the applause from the audience, this virtual applause. I would like to thank you all, the authors, again. And this concludes this first session of SIBGRAPI 2020. Thank you very much for your audience, and I hope to see you around virtually in the conference. Bye-bye.